Welcome, everyone. This is the, I would call it the first annual, first Tuesday after the Time Chains LOPSA meeting. And my name is Ben Taylor. I am your coordinator, organizer, MC for the evening. I'm formerly the Little Red Cooler Bringer of LOPSA and the LOPSA East Tennessee janitor. And now I get to be the master manipulator of the floor from home. So I feel quite honored to do that. But before we begin, I'd like to open the floor up for any announcements that you guys may have. Please, participants, feel free to raise your hand. If you have any announcements, I can bring you forward. You can tell us all about it. Announcements from the floor. Anyone? Going once. Going twice. Okay, well, it looks like we don't have announcements, but I do want to introduce, first of all, our co-organizers for the evening. We have Mr. Aaron Hahn, who is going to be our speaker for the evening. We also have Mr. Andy Cowell, who is also another one of our co-organizers. You can see them in our participants pane, most likely on, I think you guys may have a, either in chat or you may have your own participants. I don't know what it's like to be outside of admin mode here, but feel free to approach any one of them, either one of them at after the meeting, if you have any questions about anything or you'd like to speak, or for whatever reason. They're also here to serve you guys as well. We got Jonathan Evenden too. See his name there, Jonathan Evenden, Andy Cowell, Aaron Hahn, and of course myself, Ben Taylor. So. Great. If there are no further announcements or anything else that you guys may need, I'm going to go ahead and hand the floor over to our speaker, Mr. Hahn, who is going to elucidate our minds with the mysteries of blockchain. Aaron, I'm handing it off to you, sir. Thank you.
Okay, thank you very much, Ben. And I guess we should begin by managing expectations. Because my name is not Inigo Montoya, but let's first talk about if this will work. First let me fight with my.
Yes? And while you're doing that, sir, how would you like to do questions? Would you like us to just jump in with questions or hold them to the end?
Go ahead and jump them in, Ben. I will not be able to see chat, but okay. Go ahead and jump them in.
Okay, right.
There will be some asterisks in here. Some of them are inspirational, some of them are references, but most of them I'll talk about. But except this one. But it's probably best to start by talking about what this talk is not. This is not legal advice. This is not financial advice. This is also not a particularly deep dive into any one system that uses a blockchain or into how they interact with the systems around them. We're going to talk a little bit about that, and we will most certainly entertain questions about the same. At least for the presentation, though, we're not going to be talking about whether any of this is a good idea, whether the blockchain as a timestamping system itself is a good idea, or whether a given implementation is a good idea. So logically, we should now talk about what this talk is. And it's a brief overview of the blockchain in kind of a heavily reduced form. It's the 3-note version of, a symphony. We're going to talk a little bit about two of the more common systems that use blockchains, most notably Bitcoin and Ethereum. Bitcoin, namely, because it's one of the oldest, and Ethereum because it seems to approach certain things a little bit differently. Do we have anything so far? I'm also probably going a little fast.
Well, we do have, and we might be getting ahead of ourselves here, but we have a couple of questions. Well, one in particular, how do we deal with blockchain size bloat?
So I'll get to that when we talk about the implementations, because both of the implementations we're covering have different ways they attempt to reduce the amount of size, both in disk and then the contents of blocks, and mitigate either block fill to certain levels or simply make it a non-issue, as well as storage. A brief spoiler is that for most purposes, you do not actually need to store the entire chain. There are relatively few cases in which you need to do that. if you're mining and you're on Ether or Bitcoin, yes, you do. But if you're not, if you're just participating or you only need to be able to verify transactions or a subset of them, you don't actually need to store the entire chain. So let's kind of define the problem here, because a blockchain is a solution. It's not a problem. So let's say we would like a system of record of some kind. It's going to store information. And we want to be able to verify that it hasn't been broken, either intentionally or by that crappy DSL line that's always dropping packets on us. We also want it highly available to a sense. We don't want it to go down because Brad from accounting spilled coffee on the machine. We want it to be consistent as much as possible, but some of our other goals are more important than consistency. We want it to be self-validating in that the system defines its own constraints, and the constraints are part of the system and are not layered on top of it. These constraints have to be, in order to do that, the constraints have to be resolved automatically. There's no put it in the system, check if it's good, and be sad if the whole system's messed up. And a misbehaving participant shouldn't be able to skip validation. If someone tries to bring invalid data into the system, they should be turned away by everyone else. And participation is voluntary in most cases. And a single node leaving, or even a large number of nodes leaving, shouldn't jeopardize the system. This one has an asterisk because one of the trade-offs we're going to cover is results in some of this.
Here's a question.
So here we come to the actual kind of.
I've got a question here. Oh, is this a brief overview of blockchain, real quick? One of our users has asked, define blockchain in simple terms for new users.
So we're about to get to it because I have visual aids. So a blockchain, as its name might imply, is a chain of blocks. And a block is just a block of data. In this case, it can be anything. For this kind of simple demonstration, we're not even caring what's in the payload. It could be a transaction log, it could be a table, it could just be the quote of the day. However, the notable thing about this block is it has a header section or a footer section, and it contains two important pieces of information. The generation of this block, this is the first one, so it's generation 0, and the hash of the previous block. This might seem familiar if you've worked with Git before, but the next piece, and we also distribute a copy of this to our clients because we'll need it later. But the next block references the hash of this block, linking the two together. And the third block, which is block number 2, references the hash of block 1. These chains are connected, and if you compare hashes, say between 1 and 2 and 1 and 0, and that one you shipped with, you can verify that not only if all these hashes match, is the attached data is fine, but nobody's tried to mess with the data on between the point that you created it and received it. This is probably a long-winded reason to say is a blockchain in kind of its most basic is a system of pieces of connected data that refer to what came before. And in a verifiable way, refer to what came before. And as long as you have every link in the chain, each puzzle piece only fits into the block that came before. And if you have data, and if you mess with the data, the puzzle piece doesn't fit anymore. Have I answered that question? Probably not.
I think we're good. Keep talking, and we'll ask away.
Okay. The other kind of, in most systems, the blockchain itself is not really central. It's central to the operation of the system from an architectural perspective, but its function is more time-stamping. Once these blocks have been made, and once enough of them have been made, you can reasonably say that X came before Y. And that's important for our validation logic, because if we have something that says, in the currency case, you can't spend money you don't have, we need to know the order of you getting $10, giving 5 to Alice, and giving 10 to Bob. Because if you try to give the 10 to Bob first, you're fine. But if you try to give the 5 to Alice and the 10 to Bob in the wrong order, you won't have enough money. And then therefore your change should be rejected. because you're trying to spend money you don't have. In order to accomplish this, you need to determine the order of transactions. And you need to do that in a way where no one can cheat and no individual can, for the most part, direct what transactions will and won't be included, and definitely can't change the past. And there's an asterisk there, however. So back onto the main line. These hashes give us integrity verification, but not much else. The next one we're going to address is kind of skip down halfway the list and talk about high availability. If anyone's done any work with databases, this pattern of a bunch of little segments of data being put together and written, write only effectively should be somewhat familiar if you've done anything with streaming replication. Because both MySQL and Postgres, MySQL's bin logs and Postgres's wall logs, effectively operate in this manner. They don't have the same level of hash verification, but you can simply just run them on multiple machines, and each time a new piece of information is created, it's then disseminated to all of the various nodes. And only then is it considered a true piece of the record. This alone checks our high availability box, but it causes a problem because all of these participants are working off a shared set of information to be timestamped. And they might choose different items. And if there's nothing to slow them down, they're just going to keep doing it all the time. And we're going to have 530,000 servers all across the internet trying to create block 3 instead of one of them creating 3, one of them creating 4, and one of them creating 5. Which doesn't work so well for our use case. So that's kind of bad for consistency. So we have a little bit of a way we can make this, we can kind of save this. If we throw some randomness into the game here and say that in order to publish a block, you must meet some random challenge. You must do the mathematical equivalent of getting 10 nat 20s in a row or more. And only then will a block containing the proof of those 10 D20s be accepted. And you can even automatically adjust the number of D20s you have to land on 20, or coins you have to land on heads, or in the most common implementation, the number of zeros your hash has to start with, to simply allow you to mediate the rate at which blocks enter the network. Go ahead, Ben. I thought I heard a Ben.
No, we're good. No question here.
Okay. This allows you to slow the network down so that a block will have a chance to propagate, because each worker is working on the block after the most high numbered block, or tallest or deepest block, depending on what your implementation calls it, that it last received. That actually it gets us a very interesting type of consistency it's akin to eventual consistency, and it's good enough for most cases. It also helps with our whole participants problem, because a different user is likely to get those dice rolls or coin flips at the same time. No one user is necessarily always going to be producing blocks. The roll will shift around. You could think of it more as a lottery where every participant gets odds, depending in the case of Bitcoin and Ethereum, the amount of CPU or processing power, wherever it comes from, that they're donating to the pool. They have that chance to, quote, win the lottery and create the new block. If they do, they succeed. If they are unable to, then they have to try again. We could say to a point that we've decentralized the system, kind of. There's an important exception we'll have to come to in a moment. And there's really two. But the first is that, But if we continue on and we really only start caring about the machine that actually does produce that block. So, because if you didn't make the magic numbers, you didn't get the dice rolls, it doesn't matter what data you chose to include in the block. It doesn't even matter that you computed it at all. You lost the lottery. So we only really have to care about the winner. And let's say, there's some weirdness that can happen when we talk about consistency. Let's say that this one guy, he just won the lottery and he is imagining He's imagining block 4. Now, roughly at the same time, or even a moment before, another server won the same lottery. There's equal chance for everyone. There's nothing to say that two can't happen right after another. And they've made their own block 4, and it's different. Now we have to have some way to resolve this. Each miner that picks up one of these blocks, and miners are typically what we call participants in proof of work systems, because they're putting a whole lot of work and effort, all these dice rolls that don't land on 20, that they're trying to find the new block with. It's like mining through ore for gold or digging for the needle in the haystack, and only the needle can go into the blockchain. Hay can't. So which of these chains becomes the true future depends on which of them the next block comes on to. And let's say in this case, some other server produced block 5 off of this one, and then block 6 was produced off this one. And all the miners are trying to find block 7. And it's kind of sad for that first server that created the first block 4, because it might as well not exist, because the chain has continued on without it. All the data that was attached to 4 hasn't been committed to the chain. It'll have to be re-entered later. Or if you got lucky, it might be in the new 4 and 5 and 6. This is actually kind of useful. This randomness allows us to enforce validation rules pretty much globally. Let me say pretty much, in that if a block is offered by whoever wins the lottery, but the actual acceptance is determined by all of the people that are trying to mine the next block. And if no one's trying to mine a block that's a successor to your block because there's something wrong going on in your block, it will not become part of the ledger. It'll wind up like block 4 over here, and that nothing comes after it. And then eventually another chain is longer than it. Because for most of these systems, only the longest chain is considered. There's some extra stuff going in. Ether has some systems to try to compensate people who wind up screwed if they create a block and the chain just doesn't go their way, but their block was still valid. This gives us a little bit of tamper resistance in that even if you tamper with a single client, even if the client that you tampered with wins the lottery, it's not going to do you any good unless you can continually be able to tamper with all of the machines that will win the lottery in the future, or a statistically significant percentage of them. Statistically, it's a bad word. A large portion. A lot of people tend to use the term 51% attack, which is kind of a margin to say in order to pull off certain types of attacks, you need to control about 51% of the production power of a chain, but the actual number floats around because we're playing with randomness.
We have a question here.
Go ahead.
This is proof of work versus proof of stake.
So in general, proof of work means that you're doing some randomness, some work, and in most cases it's done by perform this computation that you can't easily predict the answer of. And if the answer is below this number or has these properties, you win. So for most of the current proof of work systems operate. Proof of work is kind of a weird way of putting it. But so whenever one of these machines creates a potential block, that block has a hash, and that hash has to start with a whole bunch of zeros for it to be accepted. Because that hash is effectively random, you can't predict the hash from the input without actually doing the hash. Doing the hash is the work. Because you need maybe on average billions of hashes to come across one that will work. The proof of work is the proof that you managed to find a hash that has that one in a few billion property that actually matches the validation system. So for every block hash that's valid, there are billions and billions that aren't. Billions and billions of failed attempts. So you could call it a simple lottery system, except with a bunch of D20s. I give you 15, maybe 20, 30 D20s, and you have to roll a natural 20 on every one of them. And then and only then is your block accepted and you receive the reward. Proof of stake is different. Proof of stake is more of kind of a wager system, but not really. Because proof of work means we're doing a whole lot of computational effort that doesn't actually ever produce any real value, we're wasting potentially quite a lot of power. And proof of stake is one of the alternatives. The idea with proof of stake is you take some amount of deposit. Let's say, 27 example coin. I don't know if there actually is an example coin. And other people do the same, and you seal these deposits away in some special facility of the system. And then some process is used to determine who gets to create the next block beforehand. Or everyone submits a potential block, and there's some way to determine which block is actually accepted based on how big the deposits were. So if you make a 20 coin deposit, you'll have twice the chance of someone that made a 10 coin deposit. But if you misbehave and somebody is able to prove to the system or to other users that you misbehave by trying to vote twice or publish an invalid block, you lose your entire deposit. It just ceases to exist. Or in some cases, it might be scrolled off into an account just for those purposes. And the idea being that your aversion to loss will keep you behaving properly, and anyone who misbehaves will quickly lose their funds. So there's no need to burn computational power to continue to operate the system. However, if you're starting out where no one has any money, no one has any stakes, and proof of work might be a better example for how to start a system. Have I answered the question?
I think we're good.
Okay. So let me kick back through these because far too many animations. So we're going to talk about some trade-offs.
Okay, we do have actually another one here. Sorry.
Go ahead. We'll just leave on for now.
Why don't we see more proof of stake systems? Why is proof of work popular?
Proof of work is probably popular because it's kind of hard to start a proof of stake system unless you actually have investors. And there are some interesting questions about proof of stake. If one of the potential downsides of proof of stake is that once you have a huge amount of money in the system, proof of stake favors people who have money in the system as opposed to people who are donating a real resource. Not very efficiently donating that resource, but donating it all the less. So if you have a system where nobody has any money, proof of stake can't even be done. If you do something like run proof of work for a while, then transition to proof of stake, you have to orchestrate that transition. And Ethereum appears to be attempting to do that right now, where they've been running on proof of work for quite some time. And they've started working on something that they call Casper the Friendly Finality Gadget, which is designed to eventually transition Ethereum to a proof of stake system. At the moment, it's only operating kind of in a simulation or test mode, but in the future, it's likely to be involved in maybe 1 out of every 20 blocks and eventually involved in all blocks, such that it will no longer, that holding funds of the currency and committing them to stake will be a significantly higher chance of receiving a mining award than actually building out hardware and performing the mining operations. The potential concern, however, is that mining potentially means a very large number of participants. And early in the days, it meant people would mine on their own hardware. You didn't need much hardware to get any type of payoff. There were so few people participating at the time. However, you could say we already have a modicum of centralized control in most of the major cryptocurrencies at this point through mining pools, where instead of trying that one in a few billion lottery to get a thousands of US dollars equivalent, you instead contribute resources to a pool. You can prove that you tried so many times to that pool, and then if that pool mines a block, you get a cut proportional to the amount of effort it actually took to find the block, and you get kind of a more of a guaranteed but lesser payout. Since if I pick on Bitcoin, there's only 6 blocks generated in an hour on average. There's only 6 chances in any given hour, or less than 100 in not less than 100 in a day, only a few hundred in a day. And there are a whole lot more people trying, there is a whole lot more CPUs and GPUs and ASICs trying to mine Bitcoin than a few hundred.
Another question to follow up this, and then we'll let you get moving here.
Mm-hmm.
Doesn't proof of work favor the rich too?
You could say that proof of work favors the rich as well. So in a way does proof of stake. Sorry, yes, proof of work does favor the rich, and it also favors the, I'm not sure how to say, I wouldn't say rich in wealth, but rich in certain resources. For instance, for a while, the electricity cost in this area was low enough you could actually make money mining Ethereum in this area thanks to TVA, and it's incredibly cheap power. Simply, your output from participating in a mining pool would be greater than your cost of equipment maintenance and electricity. It does favor who's willing to purchase equipment and put it forward. It potentially favors, proof of stake favors people who moved into this specific ecosystem much more than people who moved into a crypto mining system in general. Do we have any more, Ben?
Good for now.
I'm going to take that weird audio glitch as a negative. So yep. There's two trade-offs. Go ahead.
Yeah, we're good. Go ahead. Sorry.
There's two real trade-offs that are as part of our goals from earlier. And the first is bootstrapping brand new nodes. The nodes that already exist, remember their peers from last time, and for the most part can continue to bring the network up and down without any real interruption. However, when a brand new node is unpacked from its string for afterwards, RPM or Deb, it doesn't have any knowledge of any other nodes, any other active nodes. But what it does have is the address or DNS name of some designated bootstrap nodes. And whether these are reachable or not at the time, this is what the machine will attempt to connect. If it succeeds,
Aaron,
go ahead.
Hey, Aaron, sorry, there may be something wrong with your mic or something. We're having problems understanding you.
Has it been going on for a while?
No, just for the last 10 seconds or so.
I'm going to turn it off and back on.
All right.
How are we going? This is a test.
Good. Sounds good.
Okay. Let me zoom this. So if we have a network that's existed for a while and the nodes are keeping track of who their peers are, let's turn the presentation the correct way. They'll be able to, a node that's offline briefly will be able to reestablish connection. However, a brand new node that just came out of its shrink wrap or package or installer doesn't have that benefit. And because these networks are distributed and there might not even be one in your subnet, you don't have a guaranteed way to find one. So most implementations operate with a bootstrap setup. There's a number of nodes that are generally guaranteed to be on, or at least one of them will. And sometimes these are dynamically updated as part of the protocol, which, if memory serves, Ripple did this. Or in the cases of Ethereum and Bitcoin, the ones we're picking on the most, these are hard-coded into the client and updated with the client as needed. It'll attempt to connect to one of these, and every node will gossip about its peers. So the new node will then establish connections to some non-bootstrap nodes, and then in all likelihood, that bootstrap connection will be severed. But now we have the node fully integrated. The downside of this is we've centralized at least one part of the system. This authority doesn't allow you to change the chain. It doesn't really allow you to even, it doesn't allow you to falsify data or transactions because that's all cryptographically validated. But it does potentially mean that if all those nodes are unavailable or they're all unavailable within your network, the client may fail to start. So there is potential for a risk of DOS as well. Or replacing them with software that is similar to, you could potentially make a separate network just based on gossip availability. It's not a complete issue because you can, of course, manually enter an address on the client. But for the whole user experience portion, it's desirable to have a system that you can turn on and have it function without the user having to Google around for IP addresses. And I guess that brings us to the other major trade-off, which is sidechains or uncles. There's different terms for these. And so we mentioned a little bit ago that sometimes you have a chain, sometimes it'll split off. Usually those splits don't last very long, but let's say there's, somebody runs a submarine just wrong and we have a significant disconnect event. Or the Great Firewall of China starts blocking Bitcoin. So we might have a situation where two chains are operating independently. They each produce their own separate blocks with their own separate contents. And this continues for a few generations until, at this point, the network's restored. But they're still producing separate blocks. Somebody is going to produce block number 9. And the network issue has been solved. So that block number 9 is going to get broadcast to everyone, or relayed to everyone more accurately. So the question becomes, where does block 9, which block 8 does block 9 reference? Because it can only reference 1. This isn't Git. We can't reference 2. So let's spin the wheel and see what we get. And apparently the lower chain wins today. So over time, we'll also see blocks 10 and 11 will be built off of block 9. And no one will, and since block 9 has existed and been broadcast to everyone, no one's trying to make a competitor to it. You're not going to get paid for that. Now, there is something...
Sorry, interrupting you here, buddy. So can you talk about hard-coded Bootstrap nodes versus systems like DHT, distributed hash tables?
So DHT has the side effect that it's relatively noisy in general. And DHT itself doesn't actually handle the initial Bootstrap. DHT, if you've ever tried to pull a torrent with a magnet link that doesn't have an embedded tracker, you'll know that it can take 20 to 30 minutes for you to find a node. And if you've just started a client and you have no cached DHT peers, it can take hours. Unfortunately, I can't remember off the top of my head exactly how DHT bootstraps itself. I seem to remember it actually just scans for peers, hopefully. And if it finds a peer, it then gossips with that peer to find more peers, and then hopefully some of those peers have the information you want. There's some interestingness in that DHT itself. The thing that makes DHT special is that you don't have to ask every other peer where the data is. As you ask each peer, you're effectively given the... Unfortunately, I can't remember DHT internals enough right now to explain this accurately, but DHT has the same bootstrapping issue. It doesn't use hard-coded bootstrap nodes. It kind of just hopes, which is probably not the best way of putting it. I'm sorry, I'm not able to answer that very fully right now. But it's also worth noting that previous versions of Bitcoin actually used IRC to bootstrap, which is centralized in a different way. But once the number of clients started being banned from various IRC networks, the feature was eventually removed. And now it's bugging me greatly that I can't remember how DHT actually bootstraps, because I know it's kind of weird.
No problem. That's good. We're good.
Okay. Now, we alluded earlier to the so-called 51% attack, where, if someone can obtain the majority, or better yet, 70, 80, even more of the compute power available in a pool, you could do quite a lot of interesting things. So let's say for the scenario that our unfriend here had paid an extremely large amount of money to someone in block 2. And they'd like that money back. And they're not going to give back the merchandise, but they'd like that money back. And that's less money than it would cost them to capture all the more than enough compute power to brute force the network over the next, say, a week. So let's say on their own time, they make their own block 2. And that block 2 has every transaction the normal block 2 has, except the one they would rather not exist. And then they continue to do that for all the other blocks. And because they have more compute power, in theory, over averages, they will be able to get ahead of the real network. At some point, they'll be ahead. And then they'll broadcast, say, that block 12, maybe a few moments after block 11 comes out, after the real block 11 comes out. And now we'll say, hey, we're block 12. Who wants to work on block 13? And assumedly, then everyone who was mining on block 12 abandons it because block 12 has been mined. And then block 13 is mined off of block 12. And nowhere in this chain from 2 to 13 is that very expensive transaction. All history that contained it is no longer part of the main chain. The biggest trade-off of this is that there's actually no guarantee that any amount of data will remain in the chain absolutely for any amount of time. It's generally considered safe. You know, this situation where we're jumping over 12 whole blocks is incredibly way out there. Normally you would only see, even in a theoretical attack, would only be a few because you would spend money for services and then immediately turn around and double spend it. However, in this case, in our example, there's not enough compute power in the system, or in this case, proof of work system, to prevent someone from just, paying AWS a few grand and bullying everyone else out. Do we have any questions on this?
Good.
I'm going to take that as a negative. So we're going to talk a little bit about some actual specific implementations now. I've listed this as Bitcoin and Friends because there's many cases where we have a complete fork of Bitcoin with the only change being the name and what the very first block is, and then there's other things in the middle. But we're really only going to be covering this in Ethereum. Bitcoin itself uses proof of work, so it's yet more dice rolls hoping to get a magic hash that lines up. In this case, it's SHA-256, and the first n bits have to be 0. So you could say that you generate this hash, but you got to get 75 or more coins heads up all at the same time just to win. You get one block every 10 minutes about, which is relatively slow by modern standpoints, but that's not particularly important. It's really meant for as a currency system. Its payloads are actually transaction logs. There's a few other things that can go in there, but for the most part, they're transaction logs. There is a messaging system, but because it's not important in most cases to actually timestamp messages on the chain. They're just used for encryption and decryption, but they actually can be sent to the chain if desired. However, you have to pay a transaction fee for them. There's not much you can do that isn't transactions. There's a few odd cases, and people have, of course, used the comment field to do unhappy things. There is a small amount of script functionality that allows you to implement some really basic things, such as requiring two parties to send a message to a script, because there is a little bit of scripting in Bitcoin that will result in a transaction in being spendable, but they aren't particularly complicated and they don't have state. Bitcoin's also notable because it's probably one of the first successful of these types of systems. If you've only heard about one of these systems, it's probably Bitcoin. And as
question here.
As I attempt to write, go ahead.
Yeah, we have another question here. Can Bitcoin miners break crypto and hack into things with all their compute?
In theory, maybe. So Bitcoin mining equipment used to just be a normal computer. And then it was a computer with some GPUs on it. But nowadays, there are pieces of equipment that can only mine Bitcoin. The only hash they can do is SHA-256, and they might even have some weird limitations on what can go into that SHA-256 hash. So they might not be appropriate if you were going to use them to crack passwords. However, if you specifically need to solve for a SHA-256 hash where the number of bits at the beginning are 0 and keep trying really fast, and that's your password system, you could potentially use them for that. Ether, which we're going to talk about in a moment, is a lot more interesting for that case, because Ether has a lot of effort in it to make it difficult to optimize at the ASIC level. So Ether actually, in order to mine Ethereum quickly, you need a full GPU that can do anything a GPU can do. Which then means that you have to actually have that GPU, and it's just a GPU. If you can crack passwords with 5 GPUs, crack passwords with 30 GPUs, you can put on, well, I don't think I can do anything with a PCI Express lanes to do 30 GPUs, but if you can get enough GPUs, you can use it for any other computational load. But Bitcoin miners are usually very specialized, and Litecoin and a lot of the other systems that are fairly similar. Litecoin maybe not so much. Ethereum is fairly simple. Sorry, not simple. Ethereum is not simple. Ethereum is fairly similar in a few ways. It uses a hash that has to be lower than a certain number in order to be accepted. So the proof of work is that your hash is, every hash has, say, a 0.0001% chance of being lower than that number. And if it isn't, well, you don't win. You get them every 12 to 15 seconds, but that hash we talked about in a moment is very difficult to optimize for ASIC. It's actually designed to be difficult. It's got an entire gigabyte of lookup table that you have to use, and then some cache slices off of that. It is intentionally difficult to optimize. Blocks actually don't contain transactions. It's where Bitcoin, you have a giant transaction log from the beginning of time, and you figure out someone's balance by adding up all the transactions. With Ethereum, blocks actually are talking about the state of a virtual machine. That virtual machine effectively has registers for every possible account that could exist, but you can't just operate on them willy-nilly. If you just published a state that said everyone's money is now my money, no one else is going to accept that state and try to mine another block off of it. So instead of posting, say, a transaction log, you're posting more of a change log. And there's some implementation details that are notable because Ethereum actually stores the entire state for every block. So you don't actually need to hold a whole lot of history unless you're mining. There's some other optimization hacks on Bitcoin that can allow you to slowly discard pieces of the chain that you no longer need to reference, coins that have been spent, or transactions that are, transactions whose outputs are all fulfilled because no one's going to spend any money out of a transaction that has nothing in it. Though it really focuses more on non-transactional applications. Some of those are semi-transactional. You can write a simple program that says, I must receive messages from these 5 people within 20 minutes. And then and only then will I send money to wherever I was told to. Or you can implement even more arbitrary systems. A whole lot of interesting things have actually been implemented on top of Ethereum. There's actually there's actually a DNS zone that itself is hosted on Ethereum. It's only the root zone. It only does primary level delegations, but .lux, L-U-X-E, Lima Uniform X-Ray Echo, is actually hosted out of the Ethereum blockchain. And you purchase a domain on there by sending a deposit to what Ethereum calls a smart contract that takes your deposit, takes a little bit of gas to actually execute the contract and compensate the miners who are actually executing your contract for you. And then when somebody resolves that contract in the future, and since read-only operations don't cost anything because you can simulate them locally, you now have a domain that, that for all intents and purposes, no one can do anything nasty with. And you can inspect the code of the contract in question and see what it could possibly do. But without, someone really changing the architecture of the way .luxe is wired into Ethereum, it's not reasonable to do anything to the domain. And this somewhat concludes the larger portion of what I hope to cover today. So do we have any further questions? And I assume we're going to have a nice discussion, John, because this has been fairly high level, as in not getting close to the surface.
We do
have
a question here.
I'm going to jump this over here.
How does a Lightning network work?
So Lightning is complicated. Okay. I'm going to need some, I wish I had some more visual aids here, but so one of the problems that's happened with Bitcoin is the size of the block is constant, and it takes time for things to be validated. And by validated, we mean that a number of blocks have been created since that transaction was entered into the block, into the chain. So if there's, your transaction and 5 other blocks, someone would have to rewrite all these blocks to get rid of your transaction, which is really hard. But if it's just one block, and there might have been 2 candidates for that block, there's no guarantee that that will even continue to be in the chain the next day. That means that Bitcoin transactions are kind of slow, in that you announce your transaction, someone picks it up and includes it into a block, and then we wait for a few more blocks to verify that the transaction was actually done. Lightning kind of adds a layer on top of it, where you can effectively cash in some amount of Bitcoin for Lightning, and then that transaction it kind of gets passed around in weird ways, in that I'm trying to figure out how to rationalize this better, but it's effective to say that Lightning functions as an abstraction layer on top of Bitcoin, such that transactions are made on Lightning and then batched together and exchanged between different users of Lightning. What are they called? I've forgotten what Lightning calls them, but participants of Lightning effectively use Bitcoin to reconcile. The benefit of that is because with Lightning, you're dealing with entities that can respond immediately and that actually have some level of authority over the information they provide. Assuming you trust the Lightning network as participants, you can validate a transaction very quickly and only actually pay 1 transaction fee for a large block of transactions. I might be talking out the wrong end here because it's been a while since I've looked into Lightning. And the internet, because this is recorded, may proceed to shame me for it for the rest of its life.
So another question is, did you ever mine Bitcoins or own any Bitcoins?
I still hold a small amount. I have this stupid I'm an idiot story in that I tossed a full block at one point and I have no clue what it's on, and I don't think I have it anymore.
Here's another one. Can you describe an ASIC?
Okay, so an ASIC is, well, I guess I should explain the initialism first. It's an application-specific integrated circuit. So when you're dealing with, the idea is you have made a chip. The only thing it does is in this case, is compute hashes for blocks in Bitcoin. That is the only thing it does. And it is very, very good at that one thing. So you kind of have this continuum where you have a general purpose machine, like a GPU, a CPU, or a TPU if you're a machine learning guy, and it does that one very specific thing and that's it. Sorry, it does not do that. I said that backwards. It can do very general problems, except kind of TPU. In the middle, you have something called an FPGA, which people used to call programmable chips, where you can program behavior into this, and it will only be able to do the behavior you explicitly program into it, but it will probably, asterisk, be better at that than a CPU mind. An ASIC is where you actually literally go through the silicon manufacturing process and create an actual integrated circuit that just does your desired operation. There is no updating it. There is no, well, there might be microcode, but there's no firmware updates. It's a chip, and its entire job is to do this one thing, and it is completely incapable of doing anything else. You know, a Bitcoin mined ASIC is about as capable of towing a tractor as a slide rule is capable of starting a plane. That's a really bad analogy.
So here's another one. Should we be voting on blockchain? I know this is out of scope, right? Really, you said, you know.
No, I said it was only out of scope for the presentation.
Okay.
Let me exit this so I can actually see where the camera's placed. And then I, of course, turned off my mouse. Let me turn my trackpad back on. The answer is it's complicated, but that's the answer for almost everything that's wrong. So,
by the way, Mr. Guest did not ask that question.
I figured that wouldn't be his. That's not the way he words things. So, a blockchain provides a few things. The biggest thing it provides is timestamping to say, when did this happen or did it happen? You know, if I have this block from 2 weeks ago and it says something happened, I can assume that happened. You know, someone didn't make it up later. But if you have a central authority that's running, say, like a general election or an election committee, it might make more sense to have that election committee build a system, whether or not that includes a blockchain. But there's two concerns that are kind of major in most elections. The first is those only people entitled to vote, and the people that do so vote only once. Those systems are relatively easy to do when you can detach, when you have the option to, you know, say, store a ballot in an envelope with the person's name on it before you, so you validate that it is who it says it is, and you tear the name off of it, throw it in a secure box, and then later you sort them out. Because the other thing you're trying to keep track of is you don't want someone to be able to go back and see who voted for what. You want to know who voted, so you can keep them from trying to vote again. And you want to be able to figure out the totals at the end. But you don't want to be able to figure out who voted for who. And that is hard. Because if you're doing a public ledger, you could maybe, you know, you could potentially do it on a blockchain using some type of pseudonym system. So say you give every eligible voter a number for that year and some secret key to go with it. And they can, and each secret key will only be trusted for one vote entry each. And then somehow you then, you know, you make sure that you absolutely don't issue more secret keys than you should. Or maybe you, when you send those people to secret keys, if you're in a government where you have government IDs and you can encrypt them to a key stored on the government ID, you could then transmit it to a user in a way that only that user could use it, but it's not directly linked to a user. But the question still becomes, it's up to whoever's generating those tokens and keys to maintain secrecy and not keep track of who they've sent what key to. I don't really see a blockchain system solving the bigger problems that exist in voting at the moment. The systems we have now, for at least the systems we have now, with the exception of the pandemic case, and even in the pandemic case with a little bit nicer management, actually solve a lot of these problems fairly well. Now, there are some other interesting cases. Maybe voting for shares on a company might make more sense, or some other stuff, but the ability to separate those two pieces of information without entering both of them into the public record and be able to state without a doubt that person X has or has not voted, yet still not put anything in the chain that would allow someone to connect a voter's voted, have I voted status to which ballot they voted on or what the totals are, is just not an easy problem to solve regardless of how you're storing or timestamping the data.
Okay. We use blockchains to replace databases.
Only in certain situations. You could say a blockchain is a very slow key value database, or a blockchain, you know, is a database in that it stores in, as a side effect of distributing information, data is stored and disseminated. However, in most cases where you're using a database, there's not much benefit to doing it. If you're storing information that, if you're just storing information that you're the sole custodian over, a blockchain won't protect you from your own screw-ups. it'll just allow you to publicize those screw ups to all the other machines that are running them, potentially in a slower and less efficient manner than just plain old streaming replication. If you don't trust yourself, I mean, somebody has to write the software you're using to do it. For most cases, I don't see many cases where a blockchain is actually helpful. Now, I would say probably one of the best cases for a blockchain is potentially in the case where you have maybe an auction system or a financial system, something where it doesn't matter if that information was public, it doesn't matter if you've tangled it in, you want the rules to not be violated programmatically, and you don't care if it's slow, you don't care if you had to pay money to keep the miners happy, but you want everyone to be able to see everything that has happened and kind of have a higher level of transparency for it. Go ahead.
Gotcha. Well, for the kids at home, where did you get that awesome shirt?
There's a link to the website for this shirt, and the other Lands End things can be purchased through LOPSA on the membership info page at lopsa.org. And after we go back into normal mode, I shall post a link.
And I think finally, what is Satoshi Nakamoto's real identity?
I'm afraid I'm not at liberty to disclose that information.
There we go.
Yeah, I have no idea.
Okay. Cool. All right. We were also no, we're not going to ask about the books on his bookshelves.
So this is my backdrop because I moved recently, and I have built. The shelves used to hold both books and media, but now I built some bookshelves downstairs, so all the media's down there. So my bookshelves are a little bare. I mean, it's not mine to plug, but this is an interesting book.
What you need the fake books to make the bookshelves look full. Right?
No, I just need more books.
Or get more books, right? Okay, excellent.
Yeah, there's a lot of gaps, especially over on this side, because I kind of tried to order them in a way that makes some level of sense.
Nice. Well, thank you very much. Thank you very much. It was most informative and helpful, and we really appreciate you speaking for us. And everybody's applauding you right now. I am. And I guess with that, we can go back to the table.
As I looked at mystery guest, why is Litecoin different? Litecoin uses a different hash.
Oh, okay, yeah.
Litecoin uses, I believe, scrypt, which is less optimizable than SHA-256 is.
Yeah, gotcha. I didn't know if we'd lost the thread on that or not, but okay. You got the context. Okay. All right. Very cool.
Yeah. Sorry if this wasn't the usual subject matter or quite the level of polish I would have hoped, but
no, it was great, man. Thank you very much. And I'm going to go ahead and stop the recording, and we will switch back from presentation mode back to the tables and enjoy a little after party. How about that?
Yep, sounds like a plan.
All right, man. Thanks again.